Okay, crew, we are going hardcore today. Here's a differential equation with an e to the dy dx in it. Like, what is going on? What is going on? Well, let's do it. We are not afraid. Now, when I first saw this, there's one thing that came to mind, which is, oh dear Lord, why? Then I regrouped and thought to myself, how can I deal with it? Now, anything with an e to the function of y, it could be worth differentiating because then we can use the fact that the e to the something stays the same. So let's differentiate. Y differentiates to dy dx. You need to use the product rule here. So keep the x, differentiate the dy dx. So keep the x, differentiate the dy dx. Differentiate the x, keep the dy dx. And then differentiate the e, becomes e, and chain rule, we have to differentiate the dy dx. Okay, now what's nice about this, and I was very happy when I saw this happen, this happens, which is kind of cool. So we're left with 0 equals d2y dx squared times x plus e to the dy by dx. So we've got two options here. Now option number one is here. And now that one is fairly straightforward. It tells me that d2y dx squared is equal to 0. So it tells me that y is equal to ax plus b, a linear. However, this is a first order differential equation, so I shouldn't have two unknowns. Let's just plug it back in. Let's plug it back in. Left-hand side, ax plus b, and we'll get conditional b, equals x times dy dx, which is a, plus e to the dy dx, which is a. And what we notice is that, as we might think, that ax has come in, so b has to be e to the a. So it tells me that one of my solutions, solution number one, is going to be y is ax plus e to the a. Solution number one. I started with that one because it's probably the nicest one to deal with. Okay, and we can fit initial conditions, boundary conditions, because we've got a, what do you call it? A constant I can play with. I've got a constant I can play with. So this is a nice solution. It will fit this. As long as it looks like this, I can fit the a's, and it will do that, and I can fit my initial conditions. The other one I was very surprised about, and you'll see what's going to go on. So this is option number two. So we end up with e, just point out that this is what we're doing up here, e to the dy dx is equal to negative x. Now that already tells me very importantly that x needs to be negative. All right, so we're playing with negative x's here. Otherwise, this doesn't work because e is positive. So dy dx is ln of negative x. Now we need to integrate that. I'm going to times that by 1, bit of a classic here, bit of a classic. That's my v dashed, that's my u. Depending on how you like to do your integration by parts, that's entirely up to you. So y equals, when we integrate, we end up with x ln of minus x minus the integral of x times, we differentiate ln of minus x, we get 1 over x. So this becomes y equals x times ln minus x minus 1 plus some constant, which you would think, fair enough. But you would think fair enough. However, let's plug it back into here just to double check what that constant does. Let's just double check. So what I did, I was like, I'm a little bit unsure, right? The reason I did this is I always like to, when I've got, especially a first order one, like this, where you don't have to do too much, I was like, am I doing this okay? So for my own sanity, I thought, well, let's plug it back in and see what happens. And let's do that, because the result is going to be quite interesting. X ln minus x minus 1 plus c is equal to x times dy dx. dy dx was ln of minus x. So that's x ln of minus x, so that's nice, plus e to the dy dx. E to the ln of minus x minus x. And what we notice is those cancel out. So we end up with c equals 0. So what we actually have here is we have this extra solution which is only valid for x's negative. And you can't fit any boundary conditions or initial conditions, right? So it might work if your boundary conditions and your situations just about work. This is a singular solution. And this isn't like a particular integral when we look at second order, homogeneous, linear, etc. It's not, because this is not linear, right? Because of that. Because that is not linear, the solutions don't stack. If f is a solution, g is a solution, f plus g is not a solution. So it's not like I can do this plus that, right? I can't do solution 1, which will fit my boundary conditions, and add this on, because this is non-linear. This is non-linear, which is very important to note. So my general solution is down here. And if we just happen to have the correct boundary conditions, etc., 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 this is also a possible solution, only for negative x on a Tuesday, maybe, if we're lucky. But it is worth noting that it is there. Whew! Well done, my minions, my little mathmos, my little budding maths masters. Here we go. Nice, cool one here. We did not panic. We were like, yeah, do you know what? Let's differentiate. What's the worst that can happen? All right? Sometimes you just got to take a punt, and sometimes do check your answers, because sometimes by checking your answers, you get a little bit more insight as well. There we go, a little bit more from me here. Nick, doing maths. In the meantime, drop us a comment. Did you find this interesting? Do you have any questions about this whole singular solution thing? Have you encountered differential equations that have similar issues? Let me know. Subscribe, drop a comment. The bell! Do the bell. Hit the bell so that we know, or you know when the next one is coming out. To be fair, I don't really either. I'm Nick. See you next time.